So we're continuing exercise 815. We're going to draw all of the products that you could possibly get with this elimination reaction. We know it's an elimination reaction because we have a leaving group and a base. And this is really an E2 reaction because we have a strong base. So we want to predict all the products, and we want to draw all the products and also predict which one is the major product and which one is the minor product. So to do that, we need to see which are our possible beta hydrogens. Those are the ones that the base could steal. The carbon that is bonded to the leaving group, that carbon is called the alpha carbon. And every carbon next to that is a beta carbon. It's the hydrogens on the beta carbons that are going to be stolen by the base. So in this case, our base is potassium tert butoxide. That looks like this, as we discussed in that previous video for this exercise. Okay, so where do we have beta hydrogens? Well, we have one coming off of this group here. We actually have three. I'm only going to draw one to keep it visually simple. If you notice, the hydrogens coming off of here are really in the same environment. There are three other hydrogens there, but if you do the elimination with those hydrogens, you end up getting the same product as if you do the elimination with the hydrogens on top. You get a double bond toward the leaving group on a methyl group in either case. So those give you the same product, and so for the sake of simplicity, I'm just going to consider one of those things. They're kind of duplicates of each other. Finally, going to the right, the carbon chain is different, and so this will give us a different product. I'm going to draw in one of the beta hydrogens there. So there are two possibilities, because we have two different beta hydrogens here. The first possibility is that the tert butoxide comes in and steals the hydrogen on the top. And the second is that it comes in and steals the hydrogen on the bottom. So let's think about the product we get in each of those cases. If it steals the hydrogen on the top, the electrons that were keeping the hydrogen on the molecule are going to go toward the slightly positive alpha carbon. That carbon is slightly positive because the iodine is electronegative, and it's pulling electrons away from that carbon. So these electrons will go toward that slightly positive atom. It's really going to form a bond there, a pi bond, and that kicks the iodine, or the leaving group, off. So the product that you'd be left with in that case would be that. Okay, what about if it stole the bottom hydrogen? If the butoxide, the tert butoxide, stole this hydrogen, well again, these electrons will go toward the slightly positive carbon, the slightly positive alpha carbon, and it's slightly positive because the iodine that it's bonded to is electronegative. And when these electrons go toward that positive charge, it pushes the iodine off of the molecule. So you get proton transfer and loss of leaving group at the same time. So it's an E2 mechanism, and the product that we're left with is this. Let me clarify that just a little bit. There we go. So these are our two possible products. Now, if you want to think about the stability of these products, which one is the Hofmann product, which one is the Zaitsev product, put dots at the two ends of the double bond and ask yourself how many carbons are coming off of those dots away from the double bond. Here we have two. So that double bond is di-substituted. Okay, we can do a similar process of thought in this bottom one, two dots at the ends of the double bond. How many carbons are coming off of that? 1, 2, 3. So that's going to be tri-substituted. So the tri-substituted product is more stable. The electrons in that pi bond can leak into the sp3 orbitals through hyperconjugation in more ways. So that's more stable. And the di-substituted product is less stable. And when I talk about that, when I'm saying it's more or less stable because of that hyperconjugation, if that doesn't sound familiar, go back and watch that video talking about the classifying different types of double bonds and using that to describe their stability. The term hyperconjugation will come back a lot, especially in organic chemistry too. So you have this di-substituted and tri-substituted product. The more stable product is the Zaitsev product, and the less stable product is the Hofmann product. So we have these two products. Now, those are the two products we get. We always get those two. But which one is the major and which one is the minor? That depends on the type of base that we used. We used potassium tert-butoxide. That is a bulky base. And with a bulky base, the Zaitsev product is the minor product, and the Hofmann product is the major product. Because this Zaitsev product is more crowded, and so it's harder for the bulky base to reach this more crowded beta hydrogen. So that forms less often. It's much easier for it to reach a less crowded place, which gives you the Hofmann product. So that's the major product here. So those are the two products you get in that elimination reaction, that E2 reaction. And the major and minor products are here dependent on the bulky base. We have a major Hofmann product, a minor Zaitsev product. Now, if we think about E, in E, we actually don't have to think about the type of base that much. And the reason is because although you have 3 different beta hydrogens, they all will give you the same product. Now, to make that a little bit clearer, let me draw this molecule with each of the beta hydrogens labeled. So the carbon that is bonded to the leaving group is the alpha carbon. Each of the carbons next door to that are beta carbons. But notice the symmetry in the molecule. Each of the beta carbons have beta hydrogens on them. They have 2. I'm just going to draw 1. But if you draw the mechanism out, you'll see that those 3 beta hydrogens actually only give you 1 product. No matter which beta hydrogen the base steals, you only end up getting 1 product. Now, we can quickly draw the mechanism for those, just to prove that point. But already, because of the symmetry, we can see we're only going to get 1 product. So our base is sodium hydroxide. Now we have metal that gives its electrons away to whatever it's bonded to here, the oxygen, and so OH is going to serve as our base. You can have this base steal either of the 3 beta hydrogens. We'll see that each one of these is going to give us the same product. So this can steal this first beta hydrogen. The electrons go toward the leaving group and kick the leaving group off. In which case, we end up getting this as our alkene. And notice I'm drawing this side as trigonal planar because this carbon here is sp2 hybridized and so trigonal planar. You might at first have been tempted to draw it as like a group down there, but I just moved that up so that it looks trigonal planar. You could have the OH attack this beta hydrogen. It goes toward the leaving group, kicks the leaving group off. In which case, we would get that, or I should say, in which case we would get this alkene, right? The group on the right stays the same. The group on the left just gets pushed up a little bit, so it's trigonal planar, and this group at the bottom gets its pi bond. Oops. Oh. So notice that that really is the same as that product above. These two are really the same molecule. If you take this and you flip this over, and then you flip it up, if you take this and you sort of flip this up like a pancake, so this is going in 3 dimensions, you move that so that's going up, you end up with this same molecule below. And just really, really quickly, we can see how this will give us the same product again. If you take that hydrogen, it goes to form a pi bond toward the leaving group, kicks the leaving group off, And so we get that similar looking thing. So in each of these cases, we only get one product. They are all the same product. So it doesn't really matter the fact, because there's no option, we don't have a major and minor product. All three of the possible products, where you take off those beta hydrogens, all three of those beta hydrogens give you the same product. So there's only one, and that one is this. So kind of a fluke of a question. But the big takeaway is, if ever branches are all exactly the same, there's only one possible product, if the branch is going away from the leaving group. Now, that is the case in this next one. Here we have that same substrate. And so really, the product is the same. You end up getting that same product here. It doesn't matter that in this case we have a bulky base, whereas in this other case we had a skinny base, right? That's the only difference between E and F. Take a good look at that. See that it's exactly the same as this. The only difference that a bulky or skinny base would make is between preferring the Zaitsev or the Hofmann product. But in order for that to happen, you have to have a Zaitsev and a Hofmann product. In this case, all of the beta hydrogens are in the same environment, and so there's only one product. And that's the only product you get, no matter what the base is. So these last two exercises are less getting you to think through the whole thought process like we did in A, B, C, and D, and more to just try to get you to appreciate why you end up getting these two different products. You get the two different products because you have beta hydrogens that are in different environments, a more crowded environment that leads to the Zaitsev product, and a less crowded environment that leads to the Hofmann product. So hopefully this in the previous video gave you a sense of how you can think through the possible products you get in an elimination reaction, and whether they're major or minor when you use these strong bases, which give rise to these E2